factor out a 2 and no.
Just plug that in.
Did we get a handout? Did we get a handout?
That's what you do.
I mean, that's what
Hit
it
the
is.
camera and unplug the cord there. So, wow, class in 2 parts. Right. As I mentioned, the topic I'd like to discuss this week in our videos is cryptography, the art of writing codes. So sending information secretly, has been an important part of, I guess, human experience for thousands of years. You think back to really one of the biggest applications during war, right? You don't want the bad guys knowing what you're doing, but you want to tell the good guys what they should be doing. So you try to send coded messages, and even the first crypto system we're going to talk about is called the Caesar shift. This was actually used by the Roman Empire, Julius Caesar, to send messages securely 2,000 years ago. So we're going to talk about classical crypto systems, like I said, so going back from 2,000 years ago up to stuff that was used during World War I and later. So I'd like to talk about the idea of encrypting messages and decrypting messages using number theory, and then in the videos I want to talk about more modern techniques like the RSA algorithm for encoding messages. So let's talk about, so I've listed 6 different classical crypto systems. So in this notation, the plain text is like the message you want to send. I'm going to write that in lowercase letters, and then the ciphertext, or the coded message, I'll use capital letters, so you can distinguish between the message and the code. So a monoalphabetic substitution cipher is when you have just one alphabet that your code alphabet, and so you're just substituting letters of the alphabet with another letter, and that's how you encode the message. So it's called a monoalphabetic, like one alphabet. So the first several are monoalphabetic substitution ciphers. The additive cipher, or called the Caesar shift, like I said, was used by Julius Caesar. They just changed every letter in the alphabet and moved it 3 letters down in the alphabet. So A became D, B became E, C became F, and so on. So I gave you the kind of this is all you would need, I guess, if they spoke English. If they don't speak English, I guess they spoke Latin. Is it the same letters in Latin? I don't know. I take Latin. The same letters? I think it is. Most of them. So these our letters come from a lot of Greek letters. I mean, you notice similarities between like sigma and S and things like that, alpha and A. Anyway, so we have these. So this is the if you want to encode a letter, you would take each letter of your plain text and write it with its substitute. So Caesar salad would be encoded as this message, FDHBD, whatever. So you notice something about the ciphertext. I took out the space between Caesar and salad in my coded message. Why is that a good idea to do that when you're encoding messages? To remove you can't tell how many words there are, right? Like, so if there's only a few words in the English language that have like 1 letter or 2 letters, and so if you left the spaces in, that would give somebody an easy attack on your code. So that's a common tool to replace.
Either that or you were using Twitter.
How was that? Is that right? I was not using Twitter. I guarantee you. Twitter. So anyways, so let's think about this more mathematically, right? As in using modular arithmetic, it's better. It would be a better way to incorporate if we had like computing capabilities to encode these as numbers. So if we numbered the letters of the alphabet 0 through 25, then you could use modular arithmetic mod 26, and you would send, to encode a message, you would send n to n plus k, where k is some shift. So like the Caesar shift, k would be the key, k would be 3 for the Caesar shift. You would just send n to n plus 3. And that would be, and so then to decrypt, you would just do the opposite. You would subtract the key 3. So you see the common theme in a lot of these crypto systems is there's a key. And if you know the key, then you can kind of unlock the message. So in the Caesar shift, the key is just the number of the shift. Okay, so there's an easy way to attack a system like this. If you knew it was a Caesar shift, how could you do it? Well, how many possible Caesar shifts are there?
25.
Yeah, 25. 26, the shifting at 0 places would be a bad choice. Or 26 would be a bad choice for your shift. So, yeah, so you can, if you knew that, you could just try all 26 possible shifts.
Is the key is called the cipher, is that correct or no?
No, the key for this cipher would be just the letter, the number k that you're shifting. So like, if I said that it was a Caesar shift was shift 3, then that's all you need to know to decrypt or encrypt.
Cipher is then the whole process.
The cipher, yeah, is just a name for a way to encipher a message or encode a message. So a cipher is just a name for a technique, right, just to encode a message. Any questions? So that's kind of neat. This is actually used, and imagine back when people not everybody could read. It's a pretty safe cipher for the NSA and all things. So number 2, the multiplicative cipher. Now we're using a little bit of number theory here, right? We got to encrypt. Now you would multiply by a number instead of adding a number. You multiply. But the problem is you want to be able to decrypt a message, so you shouldn't just multiply by anything. Like multiplying by 0 would be bad. Multiplying by 1 would be bad. So the idea is you multiply by an integer, but you want it to be a relatively prime of 26, so that it has an inverse mod 26. If it has an inverse mod 26, then you can undo that encoding message. So if there's 26. So there's 26 letters in the alphabet. So and how many numbers are relatively prime? 26. So 26 is 13 times 2. So phi of 13 is 12. Phi of 2 is 1. So there's 12 possible keys, 12 possible numbers that you can use as your multiplicative key for this cipher. But the number 1 is one of those possible 12, which is a bad choice. Okay, so that wouldn't see why, right? So practically I guess there's only 11 keys, but technically there's 12 keys for the multiplicative cipher. I worked out an example. So if you wanted to, you encode your message, you write each letter as its number equivalent, and then you would multiply it, say, by 11, and then you would get a new number, and then that would be your ciphertext. You would transmit that to somebody, and then to undo it, they would multiply by the inverse. So the inverse of k, I worked it out, is, did I work it out? Did I write it on here? Oh, I didn't write it on here. Okay. So if you want, you're multiplying. So I said if k was 11. So to decipher a number, you multiply by 11 and reduce mod 26. So if you want to find the inverse of 11, the inverse of 11 times 11 should equal 1. Should be equal to 1 mod 26. Right. So that's how you would solve for the inverse of k. What should I do all the way? Why don't you guys do that? Find the inverse of 11 mod 26. You guys have calculators? solve 11 times k inverse, and then 1 mod 26. Uh, 19.
7.
7.
Someone gives you negative one,
Yeah, 7 could be negative.
doesn't it?
Is it negative 1 inverse?
So you should. So 11 times some integer should be equal to 1 mod 26.
Oh, I thought it would be negative.
I plugged in like on the negative one, but I added 26 to it and tried that one.
Yes, it's
19?
19.
So I mean, there's many ways to do this, right? You mean, you can
Tried it.
keep adding 26 until you get to multiple 11, and then divide by 11, so that's how you guys are doing. So you just keep adding 26. When did you stop? What was it? You said 19? Was it
19 is what I got for hand.
You added 19.
I didn't.
You could do that way.
You could.
How did you do it? You plug in numbers?
I plugged in until I got negative one.
You can do
And then I used it to
the residue
try and figure
system.
out if I could figure out
Okay.
if it's possible.
Okay.
Residue system. Can you do residue system?
Yeah, you just plug in
Yeah.
numbers 1 through 26 until you get it figured out. Yeah. I was wondering if anybody saw it. You just keep adding 26 until you get
209.
what is it?
209.
209. That's a multiple of 11.
That's 208 actually. Well, no, sorry, never mind. 209. Gosh.
Is that 9? 19 times 11,
Yeah.
and then divide both sides. Now you can divide by 11 because 11 is relatively prime to 26.
Yeah.
So that can over 19. The idea is, I showed you how to encode a message. So if you had, say you wanted to encode hello, hello would be saying 7, 4, 11, 11, 14. So you multiply each one of those integers by 11, reduce mod 26, you can get the numbers 25, 18, 17, 17, 24. So your ciphertext would be ZSRRY. So if somebody gave you that message and you want to decode it, you convert it back to these numbers, 25. So just for example, let's look at 25. So if you got a Z, which is the number 25, you multiply that by 19. So what's 25 times 19?
475.
475. So it better be 7 mod.
It
It
is.
is 7, yeah.
So that's how you would undo, the multiplying by 11, you multiply by its inverse, and you get back to 7, which is an H. Okay, so that's why your multiplicative key has to be a number that's relatively prime to 26, because that's the only way that you can find its inverse. All right. Number 3 is just combination of, it's kind of affine cipher, combining a multiplicative cipher with a shift, an additive cipher, Caesar shift. So it's just a combination. You would first multiply by one of these 12 integers, and then add a number. And so you have some more possibilities. So I said, there's how many affine ciphers are possible? Well, there's 12 choices for the multiplicative k, and then the additive J, if you add J, there's technically 26. So there's 12 times 26 or 312. Some of those are really bad. If you multiply by 1 and added 0, that's bad. So. Yeah. All right. So the Vigenère cipher, then the fourth one, again, was actually used. This was created in 1586 by a French diplomat, Vigenère, and it was actually only until the 1920s was it really shown methods for attacking the Vigenère cipher. So this was used by certain various governments, probably French governments, to encipher messages. So the difference between this cipher, so the first three were called monoalphabetic. Every letter was sent to the same letter of the cipher alphabet. You only have one cipher alphabet. But the Vigenère cipher is called a polyalphabetic substitution cipher because the same letter could be encoded different ways. There's several different alphabets used. And so the key is now, instead of just one multiplicative number like 11, the key will be several multiplicative numbers, and you use them. So there's the encrypted key is called a vector, and oftentimes a vector is corresponding to a keyword. So like in this example, I'll show you. If I just knew the keyword, I said it's a Vigenère cipher with the keyword vector. Then the vector was your keyword, and the numbers were 21, 4, 2, 19, 14, 17. Okay, whatever.
12 said 20.
Okay, so your vector is this, and then so this is really it's 6 different additive shifts, additive ciphers. So the first, if you want to encode your message, the first letter in your message would be shifted by 21 spaces, 21 letters. The second one would be shifted 4 spaces, 2, 19, and so on. And then you would just keep repeating this process. So the seventh, you'd go back, and the 7th letter in your message would be encoded by a 21, shift to 21, and so on. Okay, so it's really like a combination of whatever the length of your vector, whatever the length of your keyword is, that's how many different alphabets you're using. So in this case, like the same letter could be encoded two different ways. So like if you see a T in your code, it doesn't always correspond to the same letter in the plain text. So that's another type of crypto system.
Any idea how it broke that?
Yeah, and there's techniques for all of these. What the trick is, first, so what makes it, like I mentioned, what makes it secure is if you don't know the length of the keyword, and you don't know the shifts, obviously. So those are the two kind of things. Once you find the length, then it's a lot the length of the keyword, then that's the kind of the main attack for this system. And there's ways to do that. What you do is, so you know what language is being translated, and there's like the English language. If you look at text in an English language, certain letters appear a certain amount of proportion of times. Like E is the most common letter, and things like that. So you look at you look at distributions of letters and things like that, and so you would try to. So there's several. It's well known how to attack this. I mean, I didn't want to get into all the different ways to attack that. I give you resources if you want to find out more about how to attack these. But this one is more sophisticated than the other ones. I mean, the other ones, there's so few choices of how to create this cipher that it's pretty easy to attack. You just try them all until you get something that makes sense. This one it's based on the fact that there's a distribution of letters in a given language. So you guess. You can use that to guess the length of the keyword, and then once you know the length of the keyword, then you can just start attacking it that way. Decryption is the same. You would just, the first letter you would subtract 21, the second letter you would subtract 4, and so on, so you get back to your original message. And I give you an example. Like, here's how it works. If I keep using this vector, then the first H would go to C. That's just really a coincidence that because I use the second H also goes to C because it just work out that way. But for example, the I or E, the first E will get sent to an I. The second E will get sent to X. So it's a more sophisticated cipher. Any questions about that? If we had more time, I mean, I've used this in other classes where if we all had Mathematica in a computer lab, I can send you files. It's easier to just do this all on a computer. You can attack them using Mathematica and other software. Okay, so the next one, number 5, Playfair cipher. So this was used by the British in World War I. It's a polygraphic substitution cipher. In this case, instead of a digraph or some trigraph, those are like 2 or 3 letters. So you're encoding several letters at the same time as opposed to each letter individually. So this is the Playfair cipher encodes two letters at a time, which you call a digraph. So, so here's how it works. So you pick a keyword, and that's kind of the key. So the keyword in this case, I'm going to use Playfair as the keyword. Okay. So you don't want to use Playfair because it has 2 A's. So your keyword you would take out the second A, and as I said, you start a 5x5 matrix using these letters. So P, L, A, Y, F, and I, R. So there's your keyword, and then you start with the rest of the alphabet that hasn't been used yet. So I've already used A, so there's B, C, D, E. I've already used F, so G, H. I've already used I, so, and then I and J there's no J in the Playfair cipher. So I and J are combined because you need a 5x5 matrix instead of a 20. There's no 20, square matrix with 26 entries. Anyway, so you keep going. So H, I, J and I you only use. So any I or J is encoded together the same. And then J, K. I've already used L, M, N, O. I've already used P. I've used R, T, W, X, Y. So there's this is the matrix that you use to encode messages. So you break up your message into 2-letter chunks, called digraphs. So the plain text here, I'm going to use all work and no play makes Jack a dull boy. So you break it up into two-letter chunks. So I wrote it here like AL and then LW, OR, and so on. Now I got to a point where I had 2 L's. So like for dull, it would have been LL for the digraph. So you want to split that up because you have to have 2 different letters in each digraph. So instead of LL for my digraph, you can insert any letter you want. I inserted an X and then continue. So you can't have any digraph with the same letter because what you're doing is you're going to use this matrix to switch letters when you encode. Okay. So here's how you do it. So for example, there's 3 different possibilities. So like AL, both of those letters show up in the same row. So if that's the case, you just shift them, you just encode them to the letter that's immediately to the right. So AL would get translated as YA. The A goes to Y, the L goes to A. So that's how you do it. If the digraph occurs in the same row, you would, again, you would encode each one with the letter immediately to the right. That make sense? So, give me another example. Like, say OS occurred in your plain text. Those are in the same row. So O would get enciphered with Q, and S would get sent to T. That's another example. You take the letter in your plain text and you encode it with the number, the letter exactly to the right.
Roger, sorry. You said that two of the same letters can't be in the same digraph, right?
Right.
What about I and J? Would that be similar? Would you have to break those up into IX?
Yeah, right. Exactly. The IJ occur often.
No, JI might.
JI might, right? Yeah.
Maybe you're making a movie too.
Okay, so then that's one case. Now, what if the two letters are in the same column? So, for example, OR was in my plain text. O and R in the same column. So again, you use the letters directly below it. So O gets sent to V, and R gets sent to G. So the digraph OR will be sent to you after P. Okay. So people, I mean, like I said, this was used during World War I, and any, you know, it might seem kind of tedious to do this, but the people that were hired to do this, I mean, that's all they would do. So they can do it so fast, I'm sure, even without a computer.
Shift that OR again for me, please.
Okay. O and R on the same column. So each letter gets sent to the letter below it. O gets sent to V, R gets sent to G.
Gotcha.
So OR goes to VG.
What if it was GO?
If it was GO, it would go to OB.
Okay, what if it's OB?
Not okay. It's OB.
No, I would say.
If it's OB, does the V go to the L?
If it was, yeah, it would wrap around, exactly. So OV would be sent to VL. Okay. Any questions so far? All right, the last case is what if they're not in the same row and not in the same column? So like ND was in my, N is here and D is here. So you just make a rectangle, so the N gets sent to T. You get sent to the letter in the same row and the same column as the other letter. So N gets sent to T, D gets sent to I. So it's kind of like N gets sent to T, and then D gets sent to I. So it's like a rectangle. So N gets sent to T, D gets sent to I.
Smart just to speak now.
Decryption is just that easy, just to do the opposite.
To decrypt, reverse the process.
Yes.
And they do need a T. I think it's not D. I think it's for N.
Any other questions?
And they would change the word Playfair. to
Sure.
something else.
Yeah, you definitely wouldn't use Playfair. I mean, you use some other, right. So you use any, you could just arrange the letters of the alphabet any way you want. But it's easier to pass, like I said, if you know the key, but if I tell you it's Playfair cipher, the keyword is whatever, Tuesday, then you could just make, anybody can make their own matrix, and then you go to decode.
So do you,
This was, I said, this was used by the British in World War
so
One.
this was
They're
defined as the
mathematicians.
same Roman theater, right?
This isn't like
No,
hard, this isn't
but
hard.
to be able to do it fast in the heat
It
of battle.
doesn't, you know, well,
Just like anything, you probably get good at it.
usually, yeah, people doing this stuff aren't on the front lines. They're, you know, and, you know, you have people in these, with the radio. I think they had radios in World War One, didn't they? The radios were invented before 1917. So they, you know, you just had a radio the guy, you know, whatever. So, and then World War II. I mean, World War II. The encoded messages were used heavily by both sides. You guys, that's one sides I didn't get to. We're kind of running out of time. I want to stop with the Hill cipher next, but I wanted to. It's kind of, if you guys are like into history and stuff, you probably heard of the Enigma coding cipher used by the Germans. The Allies, especially the British intelligence agency and the Americans, worked so hard to decrypt the Enigma machine that the Germans used. And the Germans, it's kind of like the Visionaire cipher where there was many different alphabets used. And it was like a typewriter, and there was rotors inside. And each time you pressed the button, one of the rotors inside would click, and so you'd have different alphabets used. And so there were so many different alphabets used because of the way it was created. And so it took hundreds of thousands probably of people working to decode that. But they said that, I've read that encoded messages that they finally were able to break, partly because they captured some of the Enigma machines from the German submarines and different bases, that it saved a year or two of the war time. It decreased the war that long because of the advantages that the Allies gained from decoding German messages. So that's kind of an interesting topic in itself, and that you can spend more time on that. But the Hill cipher, which I want to mention also because it was, even though it wasn't used extensively, it was the first crypto system that used modern algebra, so algebraic techniques extensively. So it's similar to, it's like a multiplicative cipher, but instead of multiplying each individual letter by a number, you multiply a vector by a matrix, and so the key is a matrix. And so you're doing matrix multiplication, and then you can take an inverse of a matrix, and you can undo the message that way by taking the inverse, multiplying by the inverse matrix. So number 6, the Hill cipher, it was created in 1929. Wasn't really used extensively, but like I said, it's significant that it used algebraic methods extensively. If you take the key is an n by n matrix, and you would take n letters of your plaintext and turn it into numbers, and then you multiply that matrix, your vector, by the key matrix, and that encodes it to another vector, and that's your ciphertext. So in this case, I give you an example. So my matrix M is 1, 2, 3, 4, 5, 6, 11, 9, 8. So I would take 3 letters. So if my message was ABC, that would translate to 0, 1, 2. Then I would, to encode it, to encrypt it, I would multiply 0, 1, 2 times my key. And that would generate a new matrix. When I reduce my 26, it would be 0, 23, 22. So that would be, so my plaintext ABC would be converted to AXW using this Hill cipher. Okay, so the same issues that we occurred when we did multiplicative ciphers occur here. If you're going to undo this matrix multiplication, you have to have a matrix that's invertible. So a matrix is invertible, its determinant is not 0, but also, in this case, since we're reducing mod 26, the determinant has to be relatively prime to 26. Because if you've studied linear algebra, you can find the inverse of a matrix using this formula. It's 1 divided by the determinant of the matrix times the adjugate of the matrix M. So the adjugate has integer coordinates. So the problem is this 1 over the determinant. In congruences, you can't have fractions. So 1 over the determinant, you have to interpret that as the multiplicative inverse of the determinant mod 26. So in this example that I worked out, the determinant of m is -3, so I get this 1 over -3 that I have to deal with. Well, what I really need to do is replace that with the inverse of -3. The inverse of -3 is 17 mod 26. So instead of 1 over -3, I'm replacing that with 17. And then multiply by 17, and then reduce that matrix mod 26. So this would be how you would decode messages. This would be the inverse of this matrix, the original matrix M. So you would take each message, each vector of your ciphertext, multiply it on the right by the inverse matrix, and I did that example. So like 0, 23, 22, which is our ciphertext, we'll multiply that by an inverse matrix and reduce, you do get 0, 1, 2. We're back to ABC. Okay, that's the Hill cipher. So again, this is a little bit of history of the use of number theory in encoding messages. My videos that I'm going to post this week are going to be talking about the RSA algorithm, which was used, it's still used today, but it was used more to a greater extent from like 1977, I think about 2001. Then when techniques for breaking that cipher, breaking that code became, as computing power gets more powerful, there's going to be more techniques for breaking these codes. So the government, U.S. government went to a different system, and then they've even changed it again. So, but the RSA is still used to send some shorter information securely. Like, so one of the key ideas is if you know the key for each one of these crypto systems, you can encrypt or decrypt. So the RSA algorithm can still be used to send a key for a different system, and that's one way it's still used. There's different encryption systems used today that are much more complicated. But if you can send the key using RSA, it's still secure for that, and it's fast. It's fast enough to send smaller information, but it's not as good as sending large bits of information. So that's why the government, U.S. government, and then nations around the world kind of follow suit when whatever the U.S. government does. So I'll talk about the RSA algorithm, and I think I will talk about. So it boils down to the fact that it's hard to factor really big numbers. If you have two large primes, like a 100-digit prime times a 100-digit prime, you multiply them together, it takes a long time to factor that big number. Okay, and so that's the key to the RSA algorithm. It takes a long time to factor that, and so it might take like 22 hours or something, for example, to factor it. Well, that's more than enough time for you to transmit your credit card information and then have that information wiped out over the internet or something like that. So, that's to come, the RSA algorithm. And then next week, kind of a different topic. I want to talk about the prime number theorem and topics like that. But there's, like I said, there's only one more homework assignment on cryptanalysis. So these crypto systems and the RSA algorithm. Any questions? Nothing. All right. Wrap it up then.